Dear colleagues, good morning. I wish I would be allowed to visit our fantastic conference live, physically, and hug you all. However, while digital interactions replace face-to-face communication, helping us to keep our ties at a distance, the world becomes apparently more and more politically divided, unfortunately. I would like to draw your attention today to the statistical mechanics and thermodynamics perspective on real-world networks. For the past century, networks have captivated our attention, serving as the backbone for applications spanning from transportation and power grids to the neural network of contemporary artificial intelligence. It wouldn't be wrong to say that our entire world is networking. Networks, often comprising a multitude of nodes interconnected by edges in a graph, present significant challenges to standard mathematical modeling approaches. The traditional approach of using coupled differential equations proves impractical here, as such densely interconnected systems frequently devolve into chaos driven by numerical errors. The ergodic hypothesis offers a solution to this dilemma by equating ensemble and time averages. It replaces the dynamic description of individual changes with a probabilistic description within the ensemble over an extended period of time, thereby circumventing the complexities of chaotic behavior. Switching temporal and ensemble perspectives under the spell of ergodic hypothesis is assumed in thermodynamics, equilibrium statistical mechanics, and the theory of dynamical systems as well. In the thermodynamic limit, thermal fluctuations become negligible, and all thermodynamic quantities, such as pressure and energy, become simply functions of the thermodynamic variables, such as temperature and density. The initial application of thermodynamic approaches to network emerged within complex network theory, where the thermodynamic limit of infinite graphs was considered, rendering graph structural fluctuations as negligible. A key focus of their discourse was the universality and ubiquity, apparent ubiquity, in fact, of scale-free graphs, which were found to be prevalent across various domains. These graphs grew according to the preferential attachment mechanism, often referred to as the Matthew principle, encapsulating the idea that rich get richer. Indeed, if we assume that new nodes preferentially connect to those with higher degrees and in proportion to an exponential factor termed fitness, then the distribution of links among nodes with a given energy or attractivity, epsilon, adheres to the familiar Bose-Einstein statistics. As a result, they observed the Bose-Einstein condensation in networks. The fittest node gets the most edges, following the naive interpretation of natural selection by Herbert Spencer, fittest survive. Nowadays, we understand that complex network theory is of a limited relevance to real-world networks. First, it is almost certain that an infinite preferential attachment graph forms a scale-free tree devoid of cycles, whereas cycles are essential for feedback mechanisms crucial to the proper functioning of real-world networks. Second, most real-world networks are finite and often quite small, with structures meticulously shaped by their functions, far from being random. Finally, from the network evolution perspective, Bose-Einstein condensation corresponds to stabilizing selection featuring nodes of high centrality of fitness. The simplistic stabilizing selection approach in complex network theory overlooked the crucial disruptive selection mechanism that fosters innovation and novelty. Today, I will discuss an alternative thermodynamic approach to networks, known as dynamic complex networks, which is based on the thermodynamic limit of exceedingly long walks. While the graph itself may be finite and even small, the length of these walks extends to infinity. For infinitely long walks, fluctuations of global graph quantities, such as the exponential growth rate of the number of distinguishable walks per step that a physicist would call a chemical potential, become negligible, so that these quantities become simply functions of the graph thermodynamic variables, such as the graph spectral radius and the graph eigenvector centrality. Long walks are very sensitive to structural defects and boundaries in graphs. Therefore, they help to address the problems of predictability, such as navigability in complex structures and automated detection of symmetries and communities, as well as to address the problems of dynamics, such as possible structural modifications and transportation in networks. Missing nodes and edges may dramatically reduce the number of very long walks available in a graph, reshaping the global mobility patterns in that. The logarithm of the number of walks plays the role of free energy in this theory. Statistical changes in mobility patterns due to graph defects that can be described conveniently in terms of entropic pressure and entropic force are as follows. In the thermodynamic limit of infinite walks, a missing node results in a local decrement of free energy by the amount of entropic pressure related to the eigenvector centrality score, and the missing edges resulting in the transfer of Walker's mobility, quantified by the entropic force related to the ratio of eigenvector centralities, as well as the spectral radius of the graph. We highlighted the values of entropic pressure and force in a graph representing the city of Lubbock, the home city of Texas Tech University, taken from the OpenStreetMap service. The city graph comprises of 10,421 nodes representing all spaces of movement, including but not limited to residential, secondary, tertiary roads, trunk, links, and highways. The value of entropic pressure in the spatial graph of Lubbock attains maximum at the contemporary structural focus of the city, far apart from the city historical downtown. The nodes of the city spatial graph on the right-hand side are highlighted according to the elements of the Fiedler eigenvector belonging to the second largest eigenvalue of the entropic force matrix. The Fiedler eigenvector indicates the direction of the fastest decrease of the entropic force over the city spatial graph of Lubbock. The entries of the Fiedler eigenvector are almost zero everywhere except for a narrow band extending from the historical city center toward the contemporary structural focus of the city. The structural focus of the city absorbs very long walks, while the historical center anchored at the abolished city railway station expels long walks. Also, railway construction enhanced the city status of Lubbock in earlier days. Its maintenance has a continuing negative impact on the urban development, since railways barricade streets, dramatically cutting down the number of possible paths people can drive or walk and create isolated neighborhoods. As a result, Lubbock, Texas grows to the southwest, running out of the loop 289 that marked the old city boundaries in the 60s. The canonical ensemble represents the possible states of a system in equilibrium that doesn't evolve over time, even though the underlying system might be in constant motion. The chemical potential, the exponential growth rate of number of walks per step for such a thermodynamic system is nothing else but the entropy calculated over stationary distributions of various possible random walks. These random walks are defined by the raw stochastic transition matrices representing the fractions of the nth order degrees of nodes. In the thermodynamic limit of exceedingly long walks, this series of transition matrices converge to the so-called Reuel-Bowen random walks, as always expressed in terms of the graph spectral radius and the eigenvector centrality. The left major Perron-Frobenius eigenvectors of these stochastic matrices, representing the various graph centrality measures, are nothing but the stationary distributions of possible random walks defined on the graph. Indeed, graph node densities under the random walks of various strategies are very different. On the left-hand side, we have shown the node density under the usual isotropic random walks that is nothing but the degree centrality of nodes. On the right-hand side, we have highlighted the node density for the royal bone random walks. These walks are statistically confined at the most open vertex of the membrane, while the probabilities of nodes on the graph periphery are miserable. First, random walks allow to measure distances between nodes as first passage times required to travel from one node to another for the first time without loops. In fact, random walks turn graphs into probabilistic projective spaces with a well-defined first passage geometry. Indeed, if we symmetrize the stochastic transition matrices of these walks, their eigenvectors form the orthonormal bases in the n-dimensional eigenvector spaces. These eigenvectors are points on the surface of the unit multidimensional sphere, and the first passage quantities are nothing but stereographic projections of these eigenvectors from the stationary distribution of walks scaled by the inverse square roots of the related spectral gaps. These first passage quantities are as follows. First heating time required for a random traveler to reach one node from another for the first time without making loops. First passage time required for a random walker to reach a node starting from another node chosen at random with respect to the density of random walks for the first time without making loops. And finally, commute time required for a walker to reach one node from another and then return back for the first time without making loops. All these first passage quantities have the structure of Euclidean geometry. The first passage time is a squared norm of a node in the n-1 dimensional projective space. The commute time is nothing but the squared Euclidean distance between two vectors representing these nodes in the projective space. Probabilistic geometry of canonical ensembles of walks, the first passage time may be used to quantify the isolation and integration in city graphs that is important for urban sociology. Sociologists think that isolation of city neighborhoods fosters poverty and crime in their dwellers. The first passage time quantifies the global connectedness of a node with respect to the entire graph structure, as taking into account all possible paths to the node available in the graph. Also, some paths may be more probable than others. We can introduce the isolation and integration indices of the places as normalized first passage times to nodes measured in the decibel scale. The degree of isolation is assessed by the first passage times calculated with respect to isotropic random walks that are insensitive to the structural heterogeneities, defects, and boundaries of a graph. On the left-hand side, we have highlighted the isolated regions of the city graph of Lubbock. The central regions of the city, encircled by the Belt Road, have a relatively good connection, except for the northeast part of the city cut off by railways. The degree of integration is assessed using the royal bone random walks based on the intuition that areas and the places of motion well integrated into the urban fabric should belong to the majority of possible infinite walks existing in the graph, and therefore determine the dominant mobility pattern in the transportation network. On the right-hand side, we have shown the integration index in the city of Lubbock. Places hosting the lion's share of very long walks highlighted hot feature global mobility patterns in urban structures, playing the role of natural, social, and economic hubs of the city. Also located within the historic city borders, areas such as those in the northeastern portion of the city that are shut off from the center by commercial trains, significantly reducing the number of infinitely long pathways, are only sporadically incorporated into the city fabric. Due to the structural imbalance fostered by railways, relatively isolated sprawling areas of the southwest are able to statistically accumulate the bulk of possible infinite roads and move Lubbock's mobility patterns from the historic core to the southwest suburbs. Integrated isolation is not an oxymoron anymore, but the home for the wealthiest people in town. On the contrary, the northeastern portion of Lubbock, cut off by railways, are characterized by very low dark blue values of the integration index, aligned with the historical segregation patterns of spatial and land division formed early in the 20th century. These are areas where Black and Latino workers were initially settled in labor camps. In our recent study, we found a close correspondence between the calculated values of isolation index for the Texas Tech University campus and the isolation perceived by human subjects as reported by students and faculty in our longitudinal survey. In the heat map shown in the right-hand side picture, we have shown the kernel density of reports indicating the particular place in the campus as being relatively isolated. Navigability in graphs and networks is another important problem that may be addressed and solved within the thermodynamic approach involving the canonical ensembles of walks. Frequently visited sites are predicted more efficiently than those that are little frequented, especially in the long run. The more frequent a node, the more predictable the navigator's position visiting it. The degree of uncertainty of a current position of a walker in the graph is assessed by the walk's entropy that can be represented as a sum of the predictable and the unpredictable information components. Performing the information decomposition of entropy into conditional information quantities, we observe that the first two terms are predictable, but the last is not. Namely, the very first term expresses the excess entropy, the information efficacy of the path integration strategy, taking the entire walk history into account, to infer the forthcoming navigator's position. The second term describes the efficacy of land-based piloting that uses the present location of the navigator to predict her forthcoming position that can be assessed through the conditional mutual information between the present and future positions of the navigator. The remaining part, unpredictable, assess the true uncertainty about the present state of the chain that cannot be resolved by the observing the past history and that does not have any repercussions for the future development of the walk. The predictable information and the unpredictable information components have the same structure as the entropy, so that we can introduce two potentials phi and psi. One characterizes the degree of navigability to a node in the graph, another characterizes the strive this node has in the graph, imposed on the walks on the graph. The navigability score quantifies a chance that a node may be a precursor to visiting other nodes in the graph. The striving potential of a node quantifies its neighborhood exploration time. Indeed, these quantities ultimately depend upon the chosen strategy of walks. Navigability under the isotropic random walks in membrane is based on the boundaries, while for the anisotropic walks, in which all infinitely long walks are taken equiprobably, navigability is based at the center of the graph. As such, the walks are statistically confined there. The strive potentials of nodes in a barbell graph shown below attain maximum for the nodes of highest connectivity because they are characterized by the longest neighborhood exploration times. In our longitudinal survey about walkability of the Texas Tech University campus, we found that calculated navigability scores are closely related to the places reported by students and faculty as being interesting, secure, and pleasant to walk. The corresponding density kernel map of subjects reports is shown on the right-hand side. Confusing environments are not associated with safety, as they can significantly increase the risk of accidents for pedestrians, as they may struggle to navigate safely and make appropriate decisions while crossing streets or interacting with traffic. The only mismatch between the navigability scores calculated in campus and walkability assessments reported by human subjects was found in young male students considering the sport facility as an interesting zone to walk. Finally, let's discuss the problems of random modifications and transportation in networks, where we introduce the grand canonical ensemble of walks. Let me remind you that the grand canonical ensemble represents the possible states of a system exchanging energy and particles with a heat bath in thermodynamic equilibrium. The graph is considered open to modifications that are taken with a probability proportional to the exponential factor, termed as fugacity. Fugacity describes the change to the system of long walks due to adding or removing a node. In the thermodynamic limit of infinitely long walks, fugacity is nothing but the inverse eigenvector centrality of a node. The nodes of high eigenvector centrality share many very long paths and therefore are characterized by the low fugacity score and vice versa. The graph is easy to modify at the nodes that are weakly integrated into the system of very long paths the probability of observing a local fluctuation of fugacity at a node takes the form of a Fermi-Dirac distribution, which is typical for non-interacting fermions in a single particle state. The graph vertices with the inferior growth rate of infinitely long walks appear to be insufficiently integrated into the graph structure, and therefore they might be lost, or, on the contrary, acquire new connections during graph structural modifications. In these pictures, we have shown another spatial graph representing the spaces of pedestrian movements in the Texas Tech University campus. On the left-hand side, we have shown the integration index on the campus calculated via the first passage times and the related fugacity scores on the right-hand side. Interestingly, the same Fermi-Dirac distribution involving fugacity also appears as the unique stationary solution of a Fokker-Planck equation describing the continuous time dynamics of distributions under the noisy transportation capacity and random edge rewiring in a graph. The continuous time evolution of a mass probability distribution of some quantity over the graph nodes is described by a forward Kolmogorov equation supplied with some initial conditions at the beginning of the diffusion process. If we add the winner process of strands beta to the forward Kolmogorov equation, we get the Fokker-Planck equation preserving the form of Kolmogorov equation up to changing from logarithms of eigenvector centrality to the Onsager potential, where centralities are modified for noisy walks. The derived Fokker-Planck equation has the Gibbs distribution as the unique stationary solution, taking the form of a Fermi-Dirac distribution of fugacity if the noise strength beta equals 1. In general, the Fermi-Dirac distribution depends on beta, and in the case of very strong noise, this stationary solution converges to a uniform distribution over graph nodes independently of the graph structure. Indeed, in this case, the traffic may get stacked anywhere. In transportation problems, we observe the typical stochastic resonance. While central hubs accumulate the most of traffic in normally operating transportation networks, as it is shown in the traffic congestion modeling on the left-hand side graph, traffic congestion may catch it at the nodes of low centrality and structural bottlenecks due to the random fluctuations of transportation capacity in networks, as is shown on the right-hand side graph. In conclusion, we briefly discussed two versions of thermodynamic approaches to complex networks. In the complex network theory, the thermodynamic limit of infinite graphs is considered. Their graphs grow following the preferential attachment approach, turning into scale-free random trees with time. In dynamic complex network approach, we considered the thermodynamics limit of infinite walks that may be defined on any very small graphs, such as triangles, for example. Graph dynamics in our approach is featured by random structural and transportation capacity modifications. While complex network theory results in Bose statistics featuring the fittest node through the Bose-Einstein condensation mechanism, dynamic complex networks are rather described by the Fermi-Dirac statistic featuring nodes of high fugacity, weakly integrated into the system of long walks, that leads to stochastic resonance, visible in traffic congestions. Thank you very much for your attention. Enjoy the conference.